Online Chloramination Monitoring and Control. What are chloramines? Chloramines are chemicals that are formed when chlorine and ammonia are combined in water. Three forms are monochloramine, dichloramine, and trichloramine. There are benefits of chloramine when compared to free chlorine. For instance, it's a more stable chemical. It's less reactive, thus reducing the formation of trihalomethanes. It has longer-lived residuals in reservoirs and distribution systems. It's an effective secondary disinfectant, and it minimizes objectionable taste and odors. Monochloramine is the desired form of chloramine. It's the most stable form. It's the least reactive, reducing the formation of trihalomethanes, and has by far the least taste and odor. This is the classic breakpoint curve, where a sample with a fixed ammonia concentration is increasingly dosed with chlorine, while the chlorine residual is measured. Here, the initial ammonia concentration is 1 milligram per liter. On the x-axis is the applied chlorine dosage, and the y-axis is the available residual chlorine as measured. On the left side of the curve, where the chlorine dosage begins, there is excess ammonia. The chlorine combines 1:1 with the ammonia to form monochloramine. This continues until all of the free ammonia is consumed. This happens at approximately a 5:1 weight ratio. As additional chlorine is dosed, it begins to decompose the monochloramine into dichloramine and trichloramine until eventually the breakpoint is reached. Any additional chlorine that is added remains in the form of free chlorine, and eventually the ammonia is broken down and the nitrogen is released as nitrogen gas. This graph represents the optimal control range of monochloramine when comparing it to the formation of flavor and total trihalomethane. The upper dashed line is the monochloramine concentration. As monochloramine concentration reaches the maximum, there is very little free ammonia in the sample. As the monochloramine concentration moves past the maximum, additional dosed chlorine decomposes the monochloramine into di- and trichloramine, which have strong taste and odor as indicated with the increase in the flavor line. These forms are also more reactive than monochloramine and will increase the disinfection byproducts, as indicated in the total trihalomethane line on the graph. To avoid this, the chlorine could be dosed at a lower ratio. Below 4:1, however, free ammonia in reservoirs and distribution may promote the formation of nitrifying bacteria. Once nitrification begins, the available chlorine residual can plummet as the disinfection demand increases. The optimal control range of monochloramine is where the free ammonia is minimum, but still measurable, ensuring the formation of di- and trichloramine is minimized. Chloramination control challenges. To maintain adequate disinfection concentration to ensure safe water. Feed enough ammonia to prevent di- and trichloramine formation and prevent drop-in chlorine residual. Prevent overfeed of ammonia to minimize the potential of nitrification in the reservoirs and distribution system. Online analysis provides the information required to control the chloramination process. Some municipalities have attempted to use free and total chlorine analyzers to control their chloramination process with limited success. As indicated on the graph, a total chlorine analyzer will give the same reading in 3 possible locations on the breakpoint curve, with no indication of which you are at. Free chlorine reacts with monochloramine, resulting in a small false reading, until we're beyond the breakpoint, where the first true indication of free chlorine is measured. Therefore, it is not possible to determine on which side of the monochloramine maximum hump the plant is operating. An ammonia measurement is required to truly predict the position on the breakpoint curve. This is the breakpoint curve as read on the ChemScan analyzer. In this case, a 0.6 milligram per liter ammonia sample was dosed with increased levels of chlorine. When the ratio is below 5:1, total chlorine and monochloramine values are equivalent. Between the ratios of 5:1 and 8:1, total chlorine is greater than monochloramine as dichloramine is formed. At ratios greater than 8:1, free chlorine is present. At ratios below 5:1, total ammonia remains constant as free ammonia decreases until reaching the 5:1 ratio. At ratios greater than 5:1, total ammonia decreases and free ammonia remains near zero. This is a slightly different representation of the breakpoint curve where the chlorine is fixed and the ammonia is varied, which better represents an actual water treatment process. Samples were prepared with an initial chlorine dosage of 3 milligrams per liter, and the ammonia concentration was decreased in each sample. While the ratio is less than 5:1, the total chlorine and monochloramine are equivalent. When we reach the 5:1 ratio, they begin to separate as dichloramine is forming. The total ammonia decreases as the graph goes from left to right, indicating the dosage of the total ammonia. The free ammonia begins at an elevated level and decreases to near zero at the 5:1 ratio. Again, the optimal control range is where the free ammonia and dichloramine are at a minimum. There are two main chloramination control strategies. The first is ratiometric control, where the chlorine to ammonia ratio is between 3:1 and 5:1. We measure the total chlorine in all forms and total ammonia in all forms, free and combined, and calculate the ratio. The second is residual control, which uses very small ammonia residual and maintains a target monochloramine. Online analysis is required to optimize either of these control strategies. ChemScan Chloramination Analyzer advantages include multiple parameter analysis, multiple sample line capability, fast analysis time, a benign waste stream, non-clogging sample system, and auto-zeroing and cleaning. The ChemScan analyzer uses benign reagents, sodium hydroxide, sodium hypochlorite, sulfuric acid, potassium iodide, hydrochloric acid, all of which are NSF 60 certified. In summary, chloramines are effective disinfectants. Monochloramine has the least taste and odor and forms the least trihalomethanes. Chloramination can be difficult to control. Too little ammonia causes di- and trichloramine formation and a loss of chlorine residual. Too much ammonia can cause nitrification in reservoirs and distribution systems. Effective online analysis equipment will aid in the control of the chloramination process.